Find the concavity intervals and inflection points for the following functions. Okay, so no intercepts and no first derivative stuff. This is going to be like a vacation. If we have df dx, why am I doing the first derivative? Because we need the second derivative, and the only way to get it is to go through this. So I'm going to get the first derivative and then just roll on into the second one. First derivative is 2x minus 8. Second derivative, d squared f over dx squared, is 2. Okay, so when we do our tests, this gets a little weird. Where is this undefined? Never. It's the number 2. It's defined everywhere. Where is this thing 0? It never is. 2 is never equal to 0. And so, very simply, this function has a positive second derivative everywhere, which means it's concave up everywhere. Now, we kind of knew that anyway because this is a parabola, and so we know the shape it's supposed to have is a U shape. It never stops being concave up. And actually, it should look more like that if it's x squared minus 8x. So this tells us some information. This confirms some things that we already knew about parabolae, but it shows that even for these cases, our second derivative tests do work. So the intervals of concavity are concave up everywhere, or on, you could say, from minus infinity to infinity if you want to be rigorous about it. And inflection points, there aren't any. This thing never inflects because the second derivative never changes between positive and negative. It's positive forever. Let's see if this one puts up more of a fight. For this f of x, I'll do prime notation for this one. F prime of x is 15x squared minus 10x. The derivative of 8 is zilch. And the second derivative is 30x minus 10. That's never undefined. Can it equal 0? Yup. 30x equals 10 divided by 30. X equals 1/3. Okay, so there's one place where this derivative, the second derivative, hits 0. I'm not at all sure that you need a table for something this simple, but just in case you want to see it. This is f double. If x is lower than 1/3, let's say it's 0, the second derivative would be 0 minus 10 is negative. At 1/3 we get 0, and if x is 500 gazillion, we get a positive value here. So this curve is concave down until we get to 1/3, and it's concave up after that. Now, if we didn't know any calculus, we would have looked at this and said, it's a cubic, it has a positive leading coefficient, and we would have presumed it had a shape something like this. And that fits what we just got from our derivative test, that it's concave down, 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 until roughly there. And after that, it kinks over and becomes concave up for the rest of its life. So the intervals of concavity would be concave down up to 1/3, concave up from 1/3 to plus infinity, and the inflection point, oh, I guess we should get coordinates for it. It's a bit of a chore, but let's be good. The x-coordinate of the inflection point is 1/3. The y-coordinate, we have to plug it into here. And we get, I'm going to clear out some space. Five times x to the third minus 5 times x squared plus 8. What do we get here? 5/27 minus 5/9 plus 8. I'm going to make that 8 over 1 because the trend is all these things are going to be fractions. Our common denominator is 27. So 5/27 minus triple both of these, and we get 15/27. Multiply both of these by 27, and we get 27 there. And 8 times 27 is 160 plus 56 is 216, if I'm not mistaken. Sorry, I just had to run that again in my head. That I was surprised. I didn't expect it to come out to that, but I guess that is right. Okay, 5 take away 15 is negative 10, plus 216 is 206/27. That should be the coordinates of our point of inflection. And that's for the cubic over here. The quadratic didn't have a point of inflection. It was concave up everywhere.